G'day, Lance from Motive Power back again with another subject as part of our off-highway vehicle design series. Today we're getting rather technical, but it could be worthwhile. We're going to talk about Terramechanics. So today it's really only a taster. This is a very technical and in-depth subject, and if you need it at that level, you need to do some research yourself. My aim today is to give you an overview of the technology that's available in case you can use it. And in off-highway, it's a fair chance you can use it, even if it's just at the concept stage to make a decision like wheeled or tracked. There are a number of very technical papers out there on the internet covering this, but there's also some good YouTube videos that I'll link down below. But first, as always, some terminology. The subject is Terramechanics. That's effectively about how to cross the ground, the mechanics of crossing the ground, if you like, the tyre-soil interface. This is grown primarily out of the military field, but it does have applications to civilian and particularly construction. Generally, you can look at it as a single pass. Will the vehicle cross this ground? For construction, it's often more important to look at it as a multi-pass, because things like loaders go back and forth over the same ground a number of times, and you need to be able to be sure that the vehicle is designed to do that on a reasonable ground. Now, there's a couple of ways that this subject's approached. Actually, a lot of different ways. The Americans, coming out of the American military, tend to use a vehicle cone index, or VCI, and that's based on cone penetrometer readings. Basically, they go out, they have a cone-shaped penetrometer, and they push it into the ground and measure the strength of soil. It's primarily for fine-grained soils and muskeg. That bit's not applicable out here. And it feeds into what's called the NATO Reference Mobility Model, NRMM. If you want to go the whole hog, you probably need to be looking at the NATO model. The British generally have followed a different path, and they use what's called MMP. Now that stands for mean maximum pressure. It'll make a little more sense in a minute. Essentially, it's the average of the pressures under each wheel. It's a simpler method of analysis, and it's quite handy, I find, for just looking at some design alternatives at concept stage. The term for all of this that's generally used is mobility. You're looking at the mobility of a vehicle, and the science behind its mobility is the Terramechanics. So why is all of this necessary? Let's have a look at some examples of why. Unfortunately, this is a bit of a dark set of images, but this is what happens when you take your Leopard 1 main battle tank into a place it wasn't designed for. I don't quite know how you tell your CO what you've done, but that would be an interesting discussion. Similar problems here. Truck was too heavy for the ice road and went through it. I'm not quite sure what happened to this Jeep, but whatever it was, that's not a good situation to be in. And we've probably all seen situations like this, where the vehicle was just too heavy for the road and has punched through it. So this sort of thing really does happen. So there are many things that actually affect mobility. Sure, the ground is important, so is the time of year, whether it's hot and dry, monsoonal, snowy. The vegetation is also important because it might stop you. The ground might be fine, but the trees might be too big. That's why a standard test for a new main battle tank is what size of tree can it knock down. And sometimes there's the oddball thing that crops up. When LAVs were first introduced to the plains on northern Australia, they're monsoonal and it's long grass. And the LAVs worked fine at high speed across the grasslands until they hit the big anthills that were hidden by the grass. They had a number of wheel stations removed by anthills. So there are other things that need to be considered as part of reviewing mobility. But today we're just going to talk about the ground and some simple ways of doing an analysis. So to me, MMP is the simplest way. And because I'm not designing for military at the moment, I can do it in a cursory way that gives me some direction for the design of the vehicle. So let's have a look at some formulae related to MMP. So here's some design notes taken from the Royal Military College of Science, Cranfield University. And here's an example of MMP, Panther tank versus a Sherman 5 Crab. Now, MMP is generally considered to be the mean maximum pressure, but I think it's actually the average of the peaks and troughs, and you'll see there. The Crab obviously has a lot higher ground pressures than the Panther as a result of the difference in road wheels. So we're looking at tracks at the moment. There are different formulas for tracks or wheels. So let's go down and look at some formulae for tracks. It's a fairly simple formula. The answer comes out in kPa. So as you can see, W is the weight on one track, M is the number of wheel stations per track, B is the track width, P is the track shoe length, and D is the road wheel diameter. So you can quickly calculate an MMP. I guess this assumes the weight is evenly balanced. There are ways of looking at individual wheel stations and combining them together, but we won't get into that at this point. And here we are with wheels. It's a very similar formula. You'll see it's a similar approach, number of wheels and so forth. This time we're talking about the section height of the tyres, the tyre radius, the tyre width, and the tyre deflection. It is very easy with this one to, I won't say confuse yourself, to convince yourself you're in a better situation than you think because you've put in an extreme radial deflection. But this sort of analysis can tell you whether you should fit a centralized tyre inflation system, a CTIS, because maybe having a tyre deflect a lot very quickly is going to really enhance the mobility. This also uses a K factor, and this is based on the number of wheels driven, the proportion of driven to undriven wheels. You'll see a little bit more about that shortly. There are a lot of different formulae for MMP. Some for track, some for wheels, some for different soils, some for different wheel types, some for different track types. And there's quite a lot into it if you get right involved. I've got a spreadsheet that I use We'll have a quick look at it. Probably a bit complicated to look at like this, but there are 3 columns of formulas for tracked vehicles, whether it's pneumatic road wheels and belt tires, or belt track, or solid wheels and link track. I've got 9 different formulae for wheeled vehicles, and they're all similar but different. The McLaren formula is probably the most commonly used at this point, but you'll see the number of inputs that can be used and different results coming out. For the purpose of today's presentation, I've simplified a lot of that down to one set of formulas. We're going to put in some numbers and we're going to see what results we get. I'm going to assume a 14-ton vehicle, tyre diameter, tyre breadth, and a deflection of 20 millimeters. Now, there's essentially 2 variables here, number of wheels and the K factor, which is based on the number of axles driven. So if we say we've got 4 wheels and they're all driven, we get an MMP of 401 kPa. I'm just going to put that down here. Now, that might be a heavy 4-wheel drive to take off-road, so let's look at making it a 6-wheel vehicle. So we'll put 6 wheels in there and we'll drive all of them. So that K factor now is still the same, and we've gone all the way down to 268. Quite a big difference just by putting more axles in, and you'd expect that. But what if I didn't want an all-wheel drive vehicle because it's more complicated and expensive? Could it be a 6x4 instead of a 6x6? Well, let's have a look at that. If it was 6x4, 2/3 of the wheels would be driven and the K factor would be 4.35. And we have 319. So it's higher than a 6x6, but might still be within your range. And for the heck of it, let's say we've got an 8-wheel vehicle and they're all driven. Now this would represent most military logistics trucks these days. 201. And we'll just make that look the same. So we basically, by going to 8 wheels, we've halved the pressure on the ground. But going to 6 wheels, we've dropped it an awful lot too. Is 6x4 worth it? Probably not. But you've now got some direct comparisons of the design of the vehicle, the concept of the vehicle. You can start to look at, is that going to be viable in the application? Now, what should the MMP be? I've just pulled up some military papers here. Heavy AFV. So we're talking about a tank. It must be less than 280. Or it must be, it's desirable to have it less than 230. So these sort of figures are readily available. And you might not be working in the military's field, but it gives you a good idea. Main battle tank basically has to go everywhere. So if you want to go everywhere, you need to have an MMP down around here. But let's look at some truck types. Now, okay, that's light AFVs, truck types. And these are primarily British nomenclature. This one is a high mobility load carrier, an improved mobility medium load carrier, etc. So essentially trucks. So for high mobility, it needs to be less than 280 MMP. To be improved but not high, 280 to 350. And as you go down to low mobility, greater than 700. So there's quite a difference. So we can actually go back into the analysis we just did there and look at our 4x4 at 401 or our 6x6 at 268. So what does that mean to us? Well, 6x6 is up in here. It's a high mobility. The 4x4 is a medium mobility. So you can immediately start to say, if you're doing an off-highway vehicle that's got to work in bad conditions, you need to get that MMP down around here. It's a good comparison. I'm obviously using a spreadsheet here. This you could do it other ways. Over time I've developed this. It's just an easy way of making sure your vehicle for mining, construction, agricultural, whatever, can cross the ground. If you get into it, you'll find there's more data available for things like tractors and log skidders and so forth, specific for those applications. But it's a great way of doing a quick comparison to make sure you're on the right track, or in fact to put you on the right track. I have barely scratched the surface today. My intent is to say to you, this stuff is available. It can be used with a little bit of prep. It can give you some good direction for your design. And it gives you the evidence that you need. If you've got someone beating you over the head to say, I only want to pay for a four-wheel drive, you can demonstrate to them that it will be a lot less mobile than a 6x6. Hard numbers. So I'd encourage you to do your own research, to come up with your own approach, and to do it, even if it's a 10-minute analysis, just to check that you're on the right design path. I've said earlier, tyre selection or the data for tyres is a big part of it. That's extremely true. You'll probably want to feed the results back into your tyre selection. That was back in episode 1. Maybe iterate a little bit. Again, it gives you the opportunity to confirm or improve your tyre selection. So once you know that the vehicle is going to be well capable of crossing the ground, that's part of your application, you can put the subject to bed and move comfortably and confidently on to the next stage of the design.